Algebra 2 people. I'm doing this while you're a couple of you over there. Hey, don't be afraid. Today it's tangents. We're going to be graphing the tangent function. And I want to be very specific about how tangent functions are different than the sines and the cosines. Actually, it's like combining sines and cosines. And then what are the basic properties of the tangent function. All right, so cosine and sines are very similar to each other. That's why we kept just talking about them together. Tangents are fundamentally different. And when we talk about tangent function, that means when we graph it and we get wiggly lines. Okay. One thing to say about tangent functions is that they're not sinusoidal. They don't have a repeating pattern like waves. They just don't look like that. They have breaks in them. They have points of discontinuity. So their shape's definitely different. Well, I'll do some stuff here with the calculators, but I want to kind of get down to the bare bones of what it is that we're doing when we get the picture. What does the picture mean? What do the lines represent? So let's start with a definition of the tangent function. Tangent function, f of theta, or f of x equals tangent theta, describes, and this is the most important thing, I think, conceptually to get, is how the slope of a line from the origin, 0, 0, out to the point on the unit circle, in general, conceptually, this is how we're going to think about it, from this point, going through some rotation of theta degrees or theta radians, how the slope changes as the angle changes. Okay? With cosine, we're looking at how, like, the bottom part of the triangle, how it gets longer and shorter as you go around the circle. And then with sine, we're looking at how high that dot is above the x-axis. But with tangent, we're going to be looking at the slope. So, you just get our imaginary slope thing here. It's obviously 0 right here. It's increasing. It's 1 at 45 degrees. And then it gets even steeper until it's right here, where it is infinite. Okay, but we will just call it undefined. There's a reason for that, because another way to define tangent is taking the sine value at an angle and dividing it by the cosine value at an angle. This again is basically the same idea as slope. And let's just try to demonstrate that. Slope is a change in y over a change in x. And on our unit circle thing, we've always been associating here cosines with changes in the x values and sines with changes in the y values. Now think about what happens to the slope if I go from here straight up. My y distance here is 1, but my x distance here is 0. So we hit a point as we're tracing the slope around the circle where we don't have a way to record what the slope is. So we know that that is an undefined situation, and we'll see that pop up on the graph of tangent as we do that. Now as we cross 90, we begin to have negative slopes. And the slope remains negative all the way in quadrant 2 until we get back to 180 degrees, and now the slope is 0. After we get past there, now the slopes are positive again, and they'll get more and more positive until we hit 270 degrees, where we have the exact same problem that we had at the top of the circle, where the slope, or sorry, the address here for sine would be -1, and the cosine is 0, which is still an undefined type of situation, right? So when we're at 90 degrees and we're at 270 degrees, whoa, where did I go? Sorry, using my function. So at the top of the circle and the bottom of the circle, I'll have this place where it's undefined again. And we'll see that, as I said, we'll see that on our graph of this stuff. Proceeding into quadrant 4, now I've got negative slopes again until I get back to where I started from, and the slope is 0. So I want you to think, what would that look like as I go to graph tangent, or I'm graphing the slope as my angle increases. Let's just do this in degrees for the weak-minded. All right, here we go, 360. What's the slope like right here? Well, it's 0. What's the slope like right there? It's undefined at 90 degrees, so we'll draw a line of discontinuity. What does it do in the meantime? It starts off where it's really, really small. It's really, really small. As we start going this way and we increase that angle, the graph is slowly climbing. What does it get to when it's here at 45 degrees? It's at 1. So it curves, and then what does it do is it keeps going, it gets more and more and more. What if we're like right there, that's like a whole lot over a whole little, and that would be a very large amount. So it just climbs and it takes off until it gets to 90, and then there's no way to calculate it. And then as soon as it's just past 90, it's super duper negative now. So it's going to start climbing from way down here until it gets back here at 135 degrees, and it'll be at -1, slope of -1. So it curves, it'll get to about here, and then by the time we get to 180 degrees, now it's back to 0. This kind of pattern will repeat itself, and so now we're basically back where we were over here, where we begin now doing vertical or positive slopes. And then once we get into quadrant 4, we're doing the same thing we did in quadrant 2, where we have negative slopes. So this picture here just gets repeated over here. And at 270 degrees, we hit another jump, point of discontinuity, and then we get this thing again. That there is 2 pi of tangent, but you notice that the period here of tangent is different than the period was for cosines and sines. I mean, for a period, we're looking through how it's gone through one of these kinds of cycles. Well, here's one of these cycles before it repeats itself again. We have like half a cycle, and then half we get back to where we started from. It only took us 180 degrees to do that rather than 360. What you see here is 1, 1.5. You have 2 full cycles and 2 pi radians. We'll get to that when we get to the properties. So I'd ask you to take your calculator. I'm going to have you set it up a very specific way so you can see the picture. If you go to your y equals, you can either type in, or maybe you should type in both. For starters, I want you to type in the fraction sine x over cosine x. Okay, for y1, type in sine x over cosine x. And in y2, I want you to type in tangent x. Okay? Oh, come on, camera. There we go. That's what I want you to put in there. And then before you hit graph, there's a couple other things that I want you to take care of. And that would be, we need to make sure that I'm going to do everything right now in degrees, so make sure you're in degree mode. And then you're going to go, instead of just going zoom 7, I want you to adjust your window, excuse me, so that it looks like this. X minimum of 0, so we can start at 0 degrees. X max of 360, so that we can go around the circle once. I want our scale to be in increments of 45 degrees. And then our y minimum, y maximum will just be -4 and 4. It could be really anything, but that'll help us see the shape of the tangent function. So I want you to set it to that. So one more thing that I want you to set before you go ahead and hit graph, and that would be, if you go second table set, it's right above the window, second table set. And I want you to set that so that it starts the table at 0 or 0 degrees, and I want it to go up by increments of 5 degrees at a time. So your table setup, I want it to be like that. Okay, you can go ahead and hit graph, and what you'll get is you know, picture like this, and those two graphs will map right on top of each other because they are exactly the same thing. Tangent is defined as it's the sine divided by the cosine, or like we said, we're just doing the slope. So there's our graph. It looks like what we've got up here on the board. Same thing. And now what I want you to do is I want you to pull up that table, your second graph, and I want you to see how the values change as you go from 0 up to 90 degrees. You can see that at 45 degrees, you hit a slope of 1. There we go. And as you continue to scroll down, you see that the numbers start to get really big really fast. A slope of 3.7, 5 point whatever. At 85 degrees, it's 11.43. And then we got at 90, it's error because it's undefined. If you want to, you can go by ones, but you're going to see that once that angle is really close to straight up, the numbers, the slope is getting really, really super big. If you keep scrolling, you'll notice that right away the slopes become negative, but they really mirror what we already saw in 85 degrees and 80 degrees and 75 degrees and so forth. It's just they're sloped down now instead of sloping up. Keep scrolling until we get to 135 and we got a slope of -1, and then we keep scrolling until we get to 180 degrees and we should be back at 0. Predict what would happen in the bottom half of the circle, right? It's going to repeat itself. It's like back where we started from. So 180 degrees looks exactly like 0 degrees. And so 185 degrees will look exactly like 5 degrees as we go around the circle. We'll see the same pattern emerge. Okay? So there's our picture for the tangent function. Let me clear the board here, and we'll get on to some of their properties. Hey there, I'm back. You're still there. So again, slope is change in y over change in x, which we're relating here on the unit circle to sine theta, cosine theta, which is our tangent function. Okay, here's our graph. There's from 0 to 360 degrees, and from that picture we can discern some of the properties of the unit circle, or sorry, of the tangent function. First is that what numbers can you put in here and get answers that come out? Well, anything, except for at the top and the bottom of the circle. And if we keep going around the circle, every time we get back to the top and to the bottom of the circle. So I have to say, we have to put an exception here that you can't put in pi over 2 or any, multiple of pi before or after that. That means like at negative pi over 2 or at negative 90 degrees, you're going to have another one of these points of discontinuity. So we could put that, or we could say 90 degrees plus every half a circle. We're going to run into one of these problems. Okay? The range is different though. The range, instead of going from 1 to -1, like the sinusoidal ones, the cosine and the sine, this one will just go on forever. Because you could, if you want, you can go to 89.999 degrees. You still get a tangent value. As soon as you hit 90, you don't. So it's the set of all real numbers. It'll go up forever. It goes down forever. The range vertically. There you go. Period. We already mentioned the period is cut in half. It only takes half as long for it to go through one full cycle. So the period for these is either pi radians, or we repeat the cycle every 180 degrees. The top half of the circle and the bottom half of the circle repeat the exact same pattern. Amplitude is kind of not really terribly useful in these types of problems. We don't see how it does it. If you manipulate your graph, if you put in like 3 tangent theta or 3 tangent x, it's just going to kind of stretch out the curve, but it's really not going to change the vertical part overall. It's just going to change the shape of the graph a little bit. And so if we kind of look at the same pieces that we had before, amplitude and period, here, actually, B kind of determines the frequency of these things. We play by the same rules, except obviously as we evaluate b here, we're going to have to think of the period differently than we did with sines and cosines. You can put anything you want to here. You can put negatives here, and it'll flip it upside down. But you are going to get one cycle between, I'm going to say this. You get one cycle of this thing between negative 90 degrees and positive 90 degrees, or negative pi over 2 and positive pi over 2. And then b gets thrown in there, and it'll squeeze them together, it'll stretch them out horizontally. The vertical asymptotes, or these limit lines here, then occur at each end of every cycle, as you can see pretty easily as you graph this thing. So that means, as far as the period goes, and you got this equation here with the b sitting there, how are you going to figure out what the period is? You're going to go pi over b is the period. So if the equation is tangent of 3x, then the period is pi over 3. If it's tangent 1x, then the period is pi over 1. Okay, that's our new rule. Instead of it being 2 pi compared to b, it's just going to be pi compared to b. And that's only for tangent. Tangent's the only one where that is the case. What about some other stuff? Well, I guess everything that you could have done to sines and cosines, you can do basically with these. You can start off with your parent function. I mean, let's say that we're throwing everything in there, right? Kitchen sink at the thing. Tangent, and then we're going to have b, and you're going to have x minus h plus k. You can still do all those things to it. This will move it, it'll shift it left or right. So there's our phase shift. There's our vertical shift. But really, you're kind of looking at these points right here as them being shifted up or down. Otherwise, it's kind of hard to tell what happened to the picture. But the same things apply to tangent as far as phase shifts and vertical shifts, as was true of sines and cosines. It's just that the amplitude looks a little bit different. You should play around with that. And this will look a little bit different because the period is only half of what it would have been with sines and cosines. The different examples ask you to then graph a new equation compared to the old equation. So keep tangent theta or tangent x in your y1 or your y2. And then just saying, did it go up, down, left, or right? Up and down, left and right is easy to tell. The changing in these ones is a little harder. You're going to have to use the formulas. But I mean, A still really is the amplitude. Okay, so use your calculator and just make the number go up, make the number go down. Compare the two equations. As you draw the pictures, you're still going to have to probably be a good idea that in the parent function, you're identifying what A is. You're saying that's the amplitude. The amplitude here is 3. Pulling out B and saying this tells me the frequency, but I'm going to use it to figure out the period of tangent function. And then remember, it's x minus the phase shift and then plus the vertical shift. The rest, again, is similar to what you've already done. So you'll be doing some things from the reteaching. You're going to have pictures like this on there. We do a little bit of graphing. I haven't done the backside yet. So, but yeah, use your calculator, use your brain. And remember, either set it for radians or for degrees, depending on the problem. And it appears that in the practice problems here on your reteaching, it's got everything listed in there in radians. Be careful about the graphs. They have a different scale on them to fit the tangent function pictures better. On 2, they already have little dashed lines in there for the points of discontinuity, or the limit lines, the asymptotes. Okay. Other than that, it's just drawing pictures. But yeah, feel free to ask questions if you need some help with the details.